the last class, we had discussed PIC processors, which were targeted primarily for low-end applications. Today, we shall start our discussions on ARM processors, which are basically 32-bit processors and are meant for particularly high-end applications. In fact, applications which involve more complex computations. If you look at history of ARM processors, it was first developed at Akron Computer Limited of Cambridge, England between 1983 and 85. It's just after 1980 when the concept of RISC was introduced at Stanford and Berkeley. Subsequently, ARM Limited was formed in 1990, and what ARM popularized is the concept of ARM core, the processor core, which they have licensed to a number of other manufacturers to make variety of chips around that same processor core. So what we shall be studying is just not a family of processors, but conceptually a CPU architecture which may figure in a number of different chips intended for embedded applications. The ARM architecture is based upon RISC architecture, but it is not a purely RISC architecture because it has been enhanced to meet requirements of embedded applications. The requirements emerge for embedded applications because I need to have high code density, low power consumption, as well as low and smaller silicon footprint. Architecturally, you will find that it satisfies various conditions and properties of RISC processors as well. It has got a large uniform register file, and it basically is a load store architecture where data processing operations are only with registers and does not really involve memory locations. It is basically a 32-bit processor, but you will find the variants of that as well. In fact, you have got ARM processors which can support both 32-bit as well as 16-bit operations. So there is a 16-bit variant embedded into a 32-bit processor. Why? We shall come to that point when we discuss thumb extension of ARM architecture. It has got good speed versus power consumption ratio and a high code density as needed for embedded systems. But where are its real exceptions or departure from classical RISC architecture? In this case, you have got variety of interesting add-on features in ARM. They have got a barrel shifter in the data path which can maximize the hardware available on chip, usage of hardware available on chip. Then there is an auto increment and auto decrement addressing modes to optimize program loops. This is not very common with RISC processors. Also, it supports load and store of multiple data elements through a single instruction, and subsequently you will find that there is an interesting set of branch instructions. In these branch instructions, they are not just individual branch instructions, but this branching can be used in conjunction with other operations. So you have got a large variety of branching possibilities. And this has also been used to maximize the execution throughput. So the basic idea is that taken a RISC core, that is basic idea of a RISC architecture, in ARM we shall find various enhancements which have been made into it to make it more suited for embedded applications. And this actually distinguishes ARM from other typical RISC processors. There are various variations of this architecture. In fact, the whole idea is that This architecture has undergone a number of versions, and these versions have been implemented into a number of processors having distinct identities and numbers. So, here we have listed 4 such versions: version 1, version 2, version 3, version 4. You will find that initially the processor was a 26-bit addressing processor. It had no multiply or provision for co-processors. The version 2 really made a 32-bit addressing mode. Version 3 really made it into a 32-bit addressing capable, and version 2 included multiply as an option. Now, this is a definite departure from PIC. PIC, like other simple microcontrollers, simply support add and subtract operations. Here in the instruction set itself, I have got multiply. In fact, we shall see also variations of multiply in the instruction set of ARM. In fact, version 4 was characterized by enhanced set of instructions, and in version 4 itself, they introduced what is called the thumb mode, and this version is called version 4T, which included a 16-bit mode. Now, this 16-bit mode obviously implies what? That given the same memory, if I can use 16-bit instructions, I can pack additional instructions. So, I can use this effectively same memory for more instructions, and thereby I can increase code density. And this is particularly useful when you really do not require 32-bit operations. And this embedding of a 16-bit variant inside the 32-bit architecture came in version, and that is being referred to as version 4T. T is for thumb. Then you had got version 5T, which is superset of 4T, adding new instructions, and the version 5TE added signal processing instructions. In fact, the instructions which are targeted for signal processing applications into the basic set. In fact, this is again a departure from classical RISC concept. Now, these architectures have been implemented into a variety of chips. So, there are some examples. ARM6 actually implements version 3. ARM7, which is a very popular ARM version, implements version 3, but another variant of this ARM7, ARM7TDMI, this actually implements version 4T. That means it has got a thumb embedded into the basic processor. The strong ARM is version 4 implementation, but this implementation is from Intel and not from ARM Limited. In fact, it has been the point I was making that ARM core has been licensed to a number of manufacturers, and they have taken the basic core, done the appropriate modifications and designed processors for various targeted applications. The example is strong ARM here, which Intel had made around the ARM core, targeted for again embedded applications. ARM9ES, this example is an implementation of the version 5TE, that is extension architecture, which implements digital signal processing instruction set, and it is primarily targeted for embedded systems which need to process lots of digital signals like speech, video, etc. Now, we shall look into the basic architecture. In fact, you have seen that once we are talking about so many variations of architecture, you will find that the ARM architecture is not synonymous with a single organization, but there are certain commonality across the different variants. We shall first look at these common features before we go into the variants in detail in subsequent lectures. First thing is, any architecture is characterized by its data path as well as by the control path. Our current focus will be on data path, and we shall try to understand the instruction set of ARM with reference to this core data path in this lecture. This data path is organized in such a way that the operands are not directly fetched from memory, because that is a basic feature of a RISC. So, the operands are typically stored in the register file, and instructions typically use two source registers and single result or destination registers wherever required. Okay. If the operation involves just two registers, then obviously the third register will not be there. But the more interesting thing is last 2 points. There is a barrel shifter on the data path which can pre-process data before it enters ALU. What is a barrel shifter? Barrel shifter is basically a combinational circuit which can shift the data bits to the left or to the right by arbitrary number of positions in the same cycle itself. If I look at a classical shift register, in a classical shift registers involving flip-flops, what happens? The number of shifts require the equivalent number of clock cycles, because the shifting takes place on the basis of clock. But here it is a combinational circuit, so that the shift takes place at one go itself. In fact, the shift takes place in the same instruction cycle. This is a very basic enhancement in the ARM data path. The other interesting feature is the increment and decrement logic, which can operate on the registers independent of the ALU. So, you have got a facility for implementation of what we call auto increment and auto decrement addressing modes. In fact, this is not uncommon with CISC processors, but this has been brought in ARM to facilitate certain operations, that is particularly block move kind of operations, and that way it is an enhancement on the key RISC model. So, let us look at the basic ARM organization. Now, what is interesting here is that this is the register bank that we were talking about. The register bank is connected to the ALU via two data paths. One is your A bus, another data path is your B bus. And this B bus goes via the barrel shifter. So, this barrel shifter can actually pre-process the data which can come from one of these source registers, and this barrel shifter can shift to the left, shift to the right, or even rotate the data before it is fed to the ALU. Now, since all of these are basically, ALU is also a combinational circuit, barrel shifter is also a combinational circuit. So, the entire, all these operations, that is the operation that ALU carries out as well as the operation that barrel shifter carries out, can take place in one cycle itself, and that actually speeds up the operation execution speed. Now, what you find here is that I can use my register bank for generation of the address as well. Okay. In fact, the PC address is PC also is part of the register bank, and that can generate the address, as well as the other register banks, okay, can be made use of for generation, for manipulation of address, because registers are in a way symmetric. They can have both address as well as the data, and they can be operated in a symmetric way. The PC generates the address for the instruction. Now, here we have not indicated whether it would be an Harvard or a von Neumann architecture typically. Okay. So, what we are concentrating primarily here, the data path. So, what you will find in this case, this incremental block enables you to decrement or increment the register values independent of the ALU. In fact, the PC value can be incremented and put back to the registers, so on and so forth. Other operations can also be done with these registers using this incrementer and decrementer block. This is the instruction decode and control, and that provides the control signals. And what you have shown here is, this is a basic block where my address bus is 0 to 31, that means it is a 32 bit. My data buses are also 32 bit. So, it is basically a 32 bit processor. It can operate on 32 bit operands, and the addresses that it generates are also 32 bit. In fact, one of the very interesting features that you should note, not only an interesting, a very basic concept here is, since my registers can handle data and address in a symmetric fashion, it is very easy to handle same number of bits for address and data and use the similar kind of operations for manipulating addresses and data in the registers. Now, let us look at this register bank, because you have found that in the data path this register bank has a very prominent role. All registers have to be 32 bits, because my data bus is 32 bit, I am operating at 32 bit operands, as well as my addresses are also 32 bits. And how many registers are there? Now, this is a very interesting question with respect to ARM processor. What I have said that in user mode, there are 16 data registers and 2 data registers which are visible. What it implies that there would be some invisible registers as well, and we shall look at this mystery slightly later on. User mode is the common operating mode. That means, when you will be running your program on ARM, typically you will be operating in user mode. And what does user mode means? It is a particular mode of operation of the processor, and therefore it implies there are other modes of operations of the processor. Data registers are typically R0 to R15, and in fact in ARM all registers are referred to by R followed by a number. So, here we are talking about data registers R0 to R15, which are visible in the user mode. Out of these registers, 3 registers perform special function. They are R13, R14 and R15. R13 is a stack pointer. So, this stack pointer refers to the entry point on the stack, and this is critical for implementation of a stack in the memory. R14 is a link register. Now, this is interesting. This is also found in variety of other processors as well. This link register is a register where return address is put whenever a subroutine is called. So, whenever a subroutine is called, the return address typically you will expect the model wise we have talked about earlier in the context of PIC, the return address goes into stack. In PIC it was a hardware stack different from the program or data area. Here we have got a single link register, and in the link register the return address is put in. Then R15 is the program counter, and obviously the current instruction what is being executed will be pointed to by the content of R15. Now, depending upon the context, registers R13 and R14 can also be used as general purpose registers, although this is not a very common usage, because you have understood that R13 and R14 has got a special role to play. Any instruction which use R0 can as well be used with any other GPR, okay? And in addition there are 2 status registers, CPSR, current program status register, and SPSR, what is called saved program status register. These are basically the status registers which are not data registers. So, here in these registers effectively the status of the current execution is being captured. In fact, the status can include status of your program as well as that of the processor. The R15, the register, is the is basically the PC. So these instructions, so this will be a 32-bit byte because that will have the address, and when it is operating in your 32-bit mode, that is not in thumb mode, all instructions will be 32-bit and the addresses are also 32-bit. And what we assume that all instructions are word aligned. That means all 32-bit instructions start at 32-bit boundary. This is very important. Okay? And what does that imply? That implies that PC value is stored effectively in bits from 2 to 31, bit numbers 2 to 31, with bits 1, 0 effectively undefined or not really useful for referring to an instruction. Now, obviously, this discussion refers to one fact, that my 32-bit address in ARM refers to byte locations. Each byte is associated with a unique address. So, if I am talking about 32-bit boundaries, that means effectively I am talking about what? Blocks of 4 bytes. So, if I have one instruction starting at location 0, then that instruction would occupy location 0, 1, 2 as well as 3. Fine. The next instruction would be located at 4. So, therefore, these two bits, the least significant bits of PC, that is R15, are in a way do not care for operations. Okay. So, that is why we say that PC value is effectively stored in bits from 2 to 31. Now, let us look at the status register, CPSR. CPSR is what is the current program status register. It has got a number of bits, again it will be a 32-bit register. It is not that all bits are used at the same time. The condition code flags which occupy the higher, that MSBs, that is most significant bits in the status register, they are standard flags which reflect various arithmetic conditions. I have got a negative flag if there is a negative result from ALU, which is typically the most significant bit. It is associated with the most significant bit. If it is 1, then it can be interpreted as a negative result when we are doing a signed arithmetic. Z indicates 0, C is a carry, and V is overflow. There is this sticky overflow flag. This is with reference to saturation arithmetic, and there is interrupt disable bits here, which are for, there are 2 levels of interrupts. We shall come to that point later on. So, we can enable or disable these 2 level of interrupts by using these 2 bits. This T bit indicates whether you are in thumb mode or not thumb mode, because when we actually have an embedded 16-bit processor into the 32-bit architecture, we shall be making use of this T bit to know whether I am operating in the thumb mode or ordinary 32-bit mode. And rest are mode bits, and these mode bits really define what is called the mode of processor's operation. The point I was discussing in terms of registers, we were telling that you can use about 16 data registers, we can use 16 data registers in your program under normal operation, and that is user mode. That mode is specified in these bits. Now, before going into these processor modes in detail, let us briefly look at this sticky overflow flag. What is saturation? Saturation means when we reach the maximum value or the minimum value because of an arithmetic operation, we may have overflow or underflow. Now, when we want to have, say for example, I have got the maximum value, say it is all 1s, and if I add 1 to it, the actually 32-bit content would become 0. Okay. Now, I may not like the 32-bit value to become 0, I may like it to stick to all ones, that is the maximum value be retained. Now, that is enabled in saturation arithmetic, and that is required for a number of signal processing tasks. In fact, the architecture 5TE has got signal processing extension, and that is why this Q flag, that saturation arithmetic flag, it becomes significant or important or relevant with respect to that architecture. The processor modes, why are these processor modes are there? They are there to define various kinds of registers, their visibility, as well as writes to what we call modify CPSR register. So, we call the processor modes either privileged or non-privileged mode. In a privileged mode, you expect to have full read-write access to the CPSR. In a non-privileged mode, only read access to the control field of CPSR, but read-write access to the condition flags. Now, try to understand this. What is the implication of this privileged and non-privileged modes? In a privileged mode, what can happen actually? In a privileged mode, since you can change the control bits, that means you can have a full read as well as write access of the control bits, you can actually change the processor mode, you can enable, disable the interrupts. So, this is a privileged operation. In a non-privileged mode, these control fields can be simply read, but cannot be changed. But the condition flags, which can change because of an arithmetic operation, would normally reflect the status of the arithmetic operation, and that should be remain write enabled even in non-privileged modes. So, typically you will find that when we talk about these kind of operations, a typical user program is expected to run in a non-privileged mode, because in a user program is normally not expected to change the control bits. And in a privileged mode, typically you will expect the OS or the supervisory shell to run. Since we are targeting for ARM for more sophisticated applications, typically there would be an OS running in an ARM based system under which user programs are expected to execute. The OS is typically expected to be running in privileged mode and user applications running in non-privileged mode. In fact, ARM has got 7 modes, and these 7 modes can be now classified as privileged and non-privileged. In fact, the privileged modes are abort, first interrupt request, supervisor, system, and another is undefined. What are they? We shall just look at. And non-privileged is user mode, and user mode is used for programs and applications. Now, privileged modes represent different scenarios. Abort is a mode when there is a failed attempt to access memory. This can happen for a variety of reasons, but and these reasons we shall look at when we consider the memory architecture subsequently, but this is a particular mode in which the processor goes in when it detects that there is a failure to access a memory location. The first interrupt request and interrupt request correspond to interrupt levels available on ARM. Okay, so when a particular kind of interrupt occurs, ARM processor goes into either first interrupt mode or interrupt request mode. Supervisor mode is a state in which processor goes in after reset, and generally it is the mode in which the OS kernel is supposed to operate, because obviously when the processor is reset, the first thing that it's expected to execute is the operating system code and not user application or program. So, this is a supervisor mode in which the processor goes in when the reset happens. The other two privilege modes are system mode and another mode is called undefined. In a system mode is a special version of user mode that allows full read-write access of CPSR. Okay. And it is also targeted for supervisory applications. Many of the OS routines can be configured to run in this system mode. The undefined mode, processor enters this undefined mode when it encounters an undefined instruction. That means, when you are trying to use an illegal opcode or undefined instruction, an instruction undefined for a particular processor, then it goes into an undefined mode. So, what you have found is that these privilege modes are primarily targeted for OS, handling of special error conditions as well as that of interrupts. And user mode is a mode intended for running user applications. Now, these modes have got associated with them a very interesting capability to manage the registers. So, we go into the concept of what we call banked registers in ARM architecture. ARM has got 37 registers in all, and typically 20 registers are hidden from program at different times. So, they are not visible registers and they are actually called banked registers. And this banked register becomes available only when processor is in a particular mode. In fact, processor modes other than system mode have a set of associated banked registers that are subset of these 16 registers that we had talked about in the user mode. Okay? And these banked registers have one-to-one mapping with the user mode registers. Okay? These banked registers have one-to-one mapping with the user mode registers. So, what happens? Let us look at this. So, I am operating, let us say, in a user mode by some means. I am in the user mode. So, in the user mode there are the 16 data registers which are available, okay, and the current program which is getting executed, that status would get reflected in the CPSR register. Now, if the processor goes into some other mode, let us say that FIQ mode. FIQ is what? First interrupt. IRQ is interrupt request mode. Now, in an FIQ mode, what we will find that I have got banked register R8, R9, R10, R11, R12 becoming available, as well as R13 and R14. What does that mean? These registers, I told you, has got a one-to-one correspondence with the registers in the user mode. That means, effectively what I am getting in a first interrupt mode, I am getting a fresh copy of R8 to R14. I am getting a fresh copy of R8 to R14. Now, what does that imply? It implies that if I am having an interrupt service routine which is operating in FIQ, that is, which is basically serving in the interrupt in the first interrupt mode, it can use R8, R9 to R14 without bothering about what happens to the original content of these registers. See, we have told you that when we want to, and you know otherwise also, that when you go to the interrupt service routine, and if I want to, from there, if I want to come back to the original program, and I have to do what? To come back to the correct state of computation, I need to store the registers in the stack. Now, storing the registers in the stack are consisting of what? Push operations that will have the overhead, and that is actually the software latency for interrupt processing. In the last class we had looked at hardware latency, this becomes a software latency. The moment I have got a fresh copy of these registers, so if my ISR do not use any other register than these, I really do not need to push these registers onto stack. So, I can minimize my software latency, and in fact that is the reason why this mode is called first interrupt mode. In other one, the interrupt request mode, what you have is simply R13 and R14 fresh copy is generated. Okay? So, other registers the copy is not generated. So, other registers you need to save if you are using them. So, obviously it is not as fast as that of first interrupt mode, because here there will be some amount of software latency which will be involved. The similar thing is true for the other modes, the supervisory mode, undefined, abort, all these modes have got a copy of R13 and R14, but other registers the fresh copy is not generated. So, these original user mode registers have to be used. If they are to be retained, they have to be saved in memory. So, what happens in case of CPSR? Now, corresponding to CPSR, what you get in these modes, what are called SPSR. So, what is SPSR? Saved program state register. So, CPSR is copied into SPSR, which becomes available in FIQ mode. So, when I return from this mode to say user mode, I have to take this content of SPSR back to CPSR, because CPSR would be storing the current status. So, when I am going back, I should have the current status of the computation back with me. So, pictorially what we say here on the about SPSR is each privileged mode except system mode has associated with it a save program status register or SPSR. This SPSR is used to save the status of CPSR when the privileged mode is entered, in order that the user state can be fully restored when the user process is resumed. This is particularly the job of SPSR. So, now if we summarize what we have said, that in the user mode I have got these 16 registers as well as CPSR. In FIQ mode, what I have got? I have got same R0 to R7 registers as that of user mode, but a fresh copy of these registers. Okay. Similar thing in IRQ have got, I can use the registers same as that of R0 to R12, but fresh copy of R13 and R14. Okay. And this CPSR is showing here. So, this CPSR is copied into SPSR, but obviously in FIQ mode I got to have a CPSR which will reflect the state of the processor in that mode during execution of that program. Okay. So, effectively what we are telling is that in these modes, if we are writing onto these registers, I shall overwrite the original data. So, if I have to save this data, if I have to get this data back, I need to save it in the stack. But in case of FIQ, I get a fresh copy of registers, so I need not save this registers value onto the stack and thereby have reduced software latency. Now, mode changes can be made by directly writing onto CPSR or by hardware when the processor responds to exception or interrupt. And to return to user mode, a special return instruction is used that instructs the core to restore the original CPSR and banked registers. The ARM memory organization, in fact ARM can be configured either in little endian form or in big endian form. And I have already told you that addresses are for each byte. Okay. So, memory addresses decrease from top to bottom and left to right, this is what it has been shown, and 32-bit word aligned is for 8 and 16-bit words also. So, all these are aligned words. Okay. So, and this configuration has been shown for little endian. Okay. And this can be configured also as a big endian processor. Now, we shall look at ARM instruction set, because we know now the data path of ARM. So, we shall see through instructions how we can use this data path. The instructions process data held in registers and access memory with load and store instructions, and that is typical of any RISC architecture. And the classes of instructions are data processing, branch, load store, software interrupt, program status register instructions, because these are the different roles. Today we shall simply look at data processing instructions. Typically, the ARM instruction set has got 3 address data processing instructions, okay, the 2 operands and 1 for destination. The other interesting feature of the instruction set is that you can do a conditional execution of each instruction. That means, depending on certain condition, you can decide whether to execute an instruction or not. In fact, these are very special kind of branch instructions, and I have told you this is an enhancement in the RISC architecture to increase the computation throughput. The barrel shifter enables shift and ALU together, so we shall have that enhancement of instruction set to do these operations. And the other interesting thing we shall look at subsequently, that you can actually increase the instruction set of the processor by adding on co-processors. And how to do that, that will be a very interesting feature for ARM architecture. Now, before we look into data processing instructions, we need to know what kind of data types are supported in ARM. Obviously, ARM is a 32-bit processor, so you will be having 32-bit word as a basic data type, but you can also look at each word as 8-bit, 4 8-bit bytes, and there can be operations on these bytes as well as 16-bit components as well. And you can configure the processor at power up as little endian or big endian, because that would define the definition of a value of a particular data, whether it is being considered as a big endian or a small endian. Now, data processing instructions obviously are concerned with manipulation of data within registers. We have move instructions, arithmetic instructions. I have indicated multiply instructions because it implements multiplication and some variants of multiplication as well. Then logical instructions, comparison instructions, this is what you standard in any instruction set of a processor. And all these instructions can have a variant with a suffix x, s or not. When you add a suffix s to an instruction, it means that the condition flags will be set appropriately depending on the condition emerging out of the computation. If it is not, if you are not using a suffix, these condition flags will not be updated. These operands are typically 32-bit wide, can come from registers or specified as literal in the instruction itself. That means I can have registers as well as immediate operands. The second operand can be sent via barrel shifter, and 32-bit result is again placed in register. Only other case is that when you really do a 32-bit multiplication, you generate 64-bit result, which can go into multiple registers. So, this is an example of a move instruction. So, move will obviously involve 2 operands, okay, and I have shown you here, this is your destination register, and n can be immediate value or source register. A simple example is R7 to R5, it means that I am moving content of R5 to R7. And there is an interesting variant of move which is MVN, that move negative. So, what you move into RD not of the 32 value from source. Okay. So, this n can be a register, can also be an immediate value. So, what you move in is not of that value into the destination. Now, we can use barrel shifter with the move instruction. Okay. And this barrel shifter can shift left, shift right, rotate right by fixed number of bits, okay. And what does it therefore help in? You can do a first multiply and division, and let us look at a simple example. Here what I have done, I have specified you move content of R5 to R7, but I have said that you do a logical shift left by 2 positions. Hash 2 indicates that immediate value 2. So, it multiplies the content of R5 by 4 and puts the result in R7. That means effectively what I have done? I have combined 2 operations into a single instruction, and that is the basic role that barrel shifter plays. So, effectively this is the whole picture. Again I am repeating, we have already seen that on the data path. So, I have got a barrel shifter, and this operand 2 comes through barrel shifter. It can be an immediate value of the operand, and I would specify the number of positions that I need to shift as part of the instruction itself. It can be an immediate value, or it can be specified in a register as well. Similarly, we have arithmetic instructions. Simple arithmetic instructions implement your 32-bit addition and subtractions. Obviously, in this case, I shall have 3 operands, 2 sources and a destination. Here I have given some example of subtraction instructions. So, I have got here the R0 sub R0, R1 and R2. It subtract the value stored in R2 from that of R1, and the result is stored in R0. In this case, this is an example of subtraction using an immediate operand, and here I have used suffix "ase", that means the result, that is the effect emerging out of this computation, would be reflected in the bits of the CPSR, but that is not true essentially in this case of in this instruction. Now, we can use these operations with barrel shifter. The moment we use them with barrel shifter, then the possibilities also increases. So, look at this. This is an example of an add instruction, and what I have done, I have added content of R1, okay, and what I have written here, I want to again do a shift by 1 position. So, if I shift by 1 position, it is effectively means what? It is multiplied by 2, and then I am adding to R1, adding to itself and putting the result back to R0. So, effectively I am multiplying the content of R1 by 3 and putting the result in R0. Okay, so, these are the various possibilities which can be there. So, you can use the barrel shifter and these operations with all of these arithmetic instructions. Next, we have multiply instructions. In fact, multiply as a block is implemented in ARM, okay, and this multiply can be looked at in 2 forms. One is called long multiply. In case of long multiply, you are expected to generate 64-bit results. Otherwise, the result is a 32-bit result. So, here we have given an example where we are telling that you multiply R1 and R2 and put the result back to R0. This is a case of a 32-bit multiplication, that is the result expected is 32-bit, so that it can be accommodated in R0. This is a case of a long multiplication and case of a long unsigned multiplication. Okay. So, you multiply the results R2 and R3 and the result is stored in R0 and R1. Okay. The number of cycles taken for execution of multiply instruction depends upon processor implementation. Okay. So, that will be architecture dependent, and you also have other than unsigned, you have got signed multiplication where the signed bit is taken care of while doing the multiplication. So, signed, you get signed long multiplication. But along with multiplication, there is another very interesting instruction which is multiply and accumulate, what is called MLA. Now, in this case what happens, I have shown the operations. If you look at here, What happens here? I am actually in this case, okay, this is an MLA, this is not a long MLA, this is an MLA with which is expected to produce 32-bit result. In this case, what happens? You actually multiply Rm into Rs, this is added with Rn, that is another register content, and the result is stored in Rd, the destination register. And when do you expect MLA operation? A very simple operation is when you do a convolution, a simple operation is convolution. When you do convolution, you actually multiply and add. And if I have to implement convolution, which is a very basic operation for a large number of signal processing tasks, then MLA becomes a very useful instruction. And that is basically the motivation for implementing MLA as an instruction in the ARM processor itself. The other variant of MLA is unsigned long MLA. So, here you have got these two registers will contain the final result, and in this case content of these registers is added with the product, and this product is expected to be a 64-bit product, and so the 64-bit product is added with the 64-bit content of the registers, and that result is stored here. There are logical instructions AND or XOR bit clear. In fact, bit clear is a very interesting instruction. In this case, this R2, I have given an example here, BIC R0, R1, R2. Now, R2 contains a binary pattern where every binary 1 in R2 clears a corresponding bit location in register R1. So, that means I can specify a bit mask. I can specify a bit mask in R2. Depending on that bit mask, the bits of R1 will be cleared and the result will be stored in R0. Okay. So, this instruction is obviously useful in manipulating status flags as well as interrupt masks, and it is something like direct bit manipulation facility. Compare instructions are another set of instructions. So, I have got simple compare, then I have got test for equality, and this test, another is test. So, you will find that depending on the operations, I have given an examples with involving registers R0 and R9. So, depending on the instruction involved, in this case of a compare, a subtraction is done, and depending on the result of the subtraction, the flags are affected, but the content of registers are not affected. In case of TEQ, there is an XOR operation, bitwise XOR operation between content of R0 and R9, and flags are accordingly changed as it gets reflected on the basis of the result obtained, but the content of R0 and R9 is not changed. This is a similar thing, and in this case use ANDing and not XOR. So, these are the typical comparison instructions available in ARM. So, what we have seen today? We have studied very basics of ARM architecture. ARM architecture is much more complex than what we have looked at today. We have understood the different modes of operation of the processor. We have examined the data path in some detail and discussed the basic data processing instructions. We shall look at other instructions, branching instructions, then software interrupt instructions, the processor status register manipulation instructions, and the other aspects of this architecture in subsequent lectures.